All right, guys, this is pre-calculus 2.2.2. So we're going to be talking more about our unit circle that we started last time. I'm going to be making a chart for it and trying to find specifically what can this tell us about sine, cosine, and tangent. So we're going to start off by making a chart here. So I'm first going to be wanting to reference the unit circle which we made the last time, this kind of deal, right? So we're going to be using this to help us kind of create this chart. So we have a chart of our radians, our degrees, and then we're going to find the cosine and the sine for each of those things. So keep in mind that our cosine is our adjacent over our hypotenuse, and our sine is our opposite over our hypotenuse. So I'm going to hop over to a docking camera. So what you would want to do is try and copy down this kind of chart onto your table. I print one off just so it looks a little bit nicer, and most of it's already done for us. So we have our degrees and our radians. The PowerPoint down there has a little bit, has those flipped, but it's the exact same thing, right? So then we have the cosine and the sine and the tangent. So for my cosine on this, right, if I want the cosine, I'm going to do the 30 degrees first, which is pi over 6, right? The cosine of this, if we used these, right, the cosine is the adjacent over the hypotenuse. So it's this length over this length here. Now this hypotenuse is 1, so then the cosine would be just rad 3 over 2 over 1, or just rad 3 over 2. So cosine be rad 3 over 2. Awesome. Okay. And then for my sine of that same angle, well, my sine is going to be my adjacent over, my opposite over my hypotenuse. So 1/2 over 1. 1/2 over 1 is just going to be a half. So then my sine is going to be 1/2. We're not going to do the tangent column yet. That's just kind of spoilers. Next thing, which we're going to be adding to our chart here. So if I go back to this, 0 is kind of so easy it's hard in a sense, right? For this length here, my hypotenuse is 1. If I think about it being like a very, very small triangle like this, where this angle is 0 and this is 1 and this is 1, this would be 0, right? So my cosine, which would be adjacent over hypotenuse, or 1 over 1, then my sine would be 0 over 1, or 0. So my cosine would be 1, my sine would be 0. Now looking at all of the rest of these, we can kind of go through and say, well, 45 degrees, my adjacent would be rad 2 over 2 over 1, and then my sine would be rad 2 over 2 over 1. Or rad 2 over 2 for both of those, because it's just all over 1. Now you're hopefully seeing a bit of a pattern here, right? It's always going to be over 1 because my hypotenuse is always a 1. That's kind of why we had this unit circle, because it's always over 1. Makes this part a whole lot easier for us. So now that we have that, we also may have learned, hey, I'm just getting the same things as I got here the last time, right? My x and my y coordinates. So my x coordinates, those were always giving me my cosine. My y coordinates are always giving me my sine. So I can really just take a look at my unit circle chart here. So I'm gonna sneeze. Okay, sorry. Safety for having to hear me sneeze. Okay, so I can just go through and say, well, at pi over 3, the cosine would be the 1/2. The sine would be the 3/2. Sorry, rad 3 over 2. And then I can go through and fill that out for the entire table. So I'm going to pause and do that, and then you go ahead and do it for yours as well, and then you can come back and just kind of check yours against mine. All right, so here's what we should have. So if you want to just pause it and just double check and make sure that your table is the same as mine, go ahead and do that. Here's the top portion, and here's the bottom portion. Okay, so once we have that, we now have a nice little place where we can really easily reference and say, hey, what's the cosine of 5 pi over 6? 5 pi over 6, cosine negative rad 3 over 2. Done. So that's kind of why we have this nice little chart for us and why it's kind of a helpful thing. It just kind of takes the same info we have on our circle and kind of organizes it into a little bit more user-friendly of a chart for us. So now, if we take a look at part C here, we're trying to find the range of values for sine and a range of values for cosine. So looking at my chart, I can see I never get higher than 1, right? Rad 3 over 2 and rad 2 over 2 are both less than 1. So it's a half and 0. So the highest that I ever get is 1. Lowest that I ever get is negative 1. Likewise, on sine, highest I get is 1. Lowest I get is negative 1. So my range, or my possible y values, my possible outputs here, are only ever between 1 and negative 1. And that kind of makes sense if we think about it on our circle here, right? If this is a unit circle, so its radius is 1, this is distance is 1, this distance is 1. And if we think about our cosine being the x values, then our cosine, this is as far right as we ever get, which is 1. This is as far left as we ever get, which is negative 1. And every other horizontal distance anywhere on my circle here is greater than negative 1. And everyone over here is less than positive 1. So we're always between positive 1 and negative 1 for my cosines. Likewise, for my sines, the lowest point that I can get to is negative 1. The highest point that I can get to is positive 1. So I never get a vertical or a y value, which is my sine, that is outside of my range of negative 1 to positive 1. So hopefully that kind of makes sense why we're kind of being restricted into that kind of region for my range for both sine and cosine. All right, let's take a look at the next part here. So this is where we're going to try and take a look at 57. They're going to try and say, well, what if we scale this up, right? So if we made it 3, right, since we saw that our y values were always our sines and our x values were always our cosines, right? Then what if we said, hey, this here would be the sine of 5 pi over 6 would equal 1/2, right? That's not going to be true. One, because the sine is the y values, not the x values there. But more importantly, which I think it's actually a typo on their part. More importantly, they're trying to get you to say, well, you don't just always use that portion, because my sine is actually a ratio, right? My sine is the ratio of my opposite over my hypotenuse, right? So my sine here would be opposite, which is going to be, they have this, I think, labeled incorrectly. I just noticed that now. But I'm just going to pull up mine. So if we went to this, right, this would be having a x value of negative 1.5 rad 3 and a y value of 1.5, right? So if I were to do the sine is the opposite over the hypotenuse. So that would be 1.5 over the radius now being 3. So then that would still give me a sine of 1/2. So the big thing that they're trying to get you to see is, even if I scale this up, and again, disregard this picture, this is the book writing that picture on. I hope it's changed in your current version. But the sine, the cosine, and the tangent, those values are consistent always and forever. Okay, those are never going to change based off of how large our circle is. If that was true, there would be no reason for us to have this unit circle, because how often are you going to have a circle with exactly a radius of 1? Rarely, if ever, right? So why we use these and why we use the unit circle is it makes the calculations really, really easy, because I'm always have a hypotenuse of 1. But if I scale things up, the ratio always stays the same. So a 1.5/3 ratio stays 1/2, which is what the sine would be at that particular point. All right, so then let's take a look at number 58. So 58, we're going to try and talk about what the tangent would be. So our tangent is opposite over adjacent, right? So looking over here, right, if this is my angle, tangent opposite, which is this y, over adjacent, which is this x, right? So I would just say it's this y value over this x value here. It's always that ratio. So then how does that relate to my sine and my cosine on my unit circle, right? On my unit circle, my x values were always my cosines. My y values were always my sines. So really this turns into the sine over the cosine. So my tangent for any given angle is going to be equivalent to my sine value, which is my y, over my cosine value, which is my x. So I can figure out any of the tangents by taking the sine, dividing it by the cosine. So let's hop back over to our table. So this is where I want you to kind of fill this out. I'll do the first few with you, and then I'll have you guys do the rest of it on your own. So for tangent of 0, right, it's sine over cosine. So 0 divided by 1 is 0. Awesome. And then if I want pi over 6, well, that's 1/2 over 3 pi over 2. So if we do a little bit of math here, 1/2 over rad 3 over 2, right? I can multiply this by the fraction 2 over 2 to get rid of those fractions inside of the fractions, and then I have 1 over rad 3, which is a little bit better. But I don't like having radicals on the bottom of fractions, so I'm going to multiply this by rad 3 over rad 3, and that gives me rad 3 over 3, because rad 3 times rad 3 is rad 9, or 3. So that's what that one's going to turn into. So I get rad 3 over 3 for my tangent value. And then 45, it's rad 2 over 2. Rad 2 over 2, well, this over this is a number over itself. That's going to be 1. That's pretty easy. And then for here, we're going to have rad 3 over 2 over 1 over 2. Very similar to what we had here, but let's do the same idea. Multiply by 2 over 2. So those are going to go away. So I get rad 3 over 1, or just rad 3. Not too bad. And then here on my pi over 2, 1 divided by 0, that's undefined because I can't divide by 0. And there we go. So what I want you to do now is to pause this video and fill out the rest of your chart for tangent, then come back here and you can check yours with mine. Go for it. All right, and here's what we should be getting. So there's kind of 2 pi over 3 down to 11 pi over 6. And then the last one we're going to get is going to be there at 0. So again, hopefully that kind of made sense. Now you should see a bit of a pattern here, right? We kind of go rad 3 over 3, 1, rad 3, undefined. Then this is going to be kind of mirrored here, and here, and here, and here. So we're kind of mirrored over this undefined point, but all of these are negative as opposed to all of these being positive. Likewise, we're kind of mirrored over this 0, Those are the same, those are the same. These are the same down to undefined, except here they're negative, here they're positive. And likewise, we're again mirrored here to here around that undefined point, but these ones being negative, those ones being positive. So those are going to be kind of key, important patterns to pick up on, and we'll talk more about those in the future. But the big thing that I want us to get right now is that chart filled out. So it's about the range of our tangent. Okay, that's kind of the last portion here. So the highest value that I saw was kind of rad 3, and then lowest being negative rad 3. But does it go beyond that, right? So if we think about our actual table here, or our graph, okay, my ratio here of my rise to my run, if I keep on going smaller and smaller and smaller, so I'm closer and closer and closer to this 0, I'm getting a very small number on top of my fraction, a very large, and close to a 1 on the bottom. So that's getting close to 0, which is why I have a tangent of 0 here. But as I approach this, right, now I'm getting closer and closer to 1 on my top, and my bottom is getting tiny, 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 tiny. So as my bottom gets super, super small, if the bottom of your fraction is like 0.00000001, right, that makes the number huge, right? So this would actually go towards infinity as I go there. So, and then vertical is when I'm undefined. So really, my range here is all real numbers, because I can go as high as I want as I get super, super close to this vertical value, and then as negative as I want as I get super, super close down to this negative vertical value, right? Because that's going to be our range in a sense. Okay, so let's hop back over here. Disregard those red dots, that's for if we do it in class. All right, so let's try this one out. So we're going to sketch a unit circle and then draw a right triangle with a base on the x-axis and a vertex at the origin, so like we've been doing for these unit circles, and then show a diagram, and then show the diagram for problem number 58. All right, so write the equation of the unit circle. Okay, what would you know about x and y in the unit circle? We write the equation in terms of sine and cosine. Okay, and then part C, the equation you found in part B is referred to as the Pythagorean identity. Why do you think it is named as such? So there's a lot there. Let's go through it. So we're going to start off with writing out the equation of the unit circle. Well, my equation for a circle is x squared plus y squared equals the radius squared, which in this case is 1 squared or 1. Okay. We could have h's and k's where it gets shifted, but this is the base form, right? X squared plus y squared means we're centered at the origin like our unit circle is, and we have a radius of 1 because it's 1 squared or again 1. So there we go. Now thinking back to what I had here, right? Was my x values were my cosines, my y values were my sines on all of those points on our table, as well as over here, right? So I could replace my x's with the cosine of the angle, which will say theta. So cosine of theta squared plus my y values were just my sines. So that could be my sine of theta squared equals 1. So then this I could write as, we typically don't write it like this. We'll typically put that little square on top of the cosine. So this would be the cosine squared of theta plus the sine squared of theta. Now I'm going to real briefly take a little side note here. I mentioned that this is how we're going to typically see it written, not like this. Why they put the actual square on the cosine and not on the end here is it can get confusing as, is it the theta that is being squared, or is it the actual entire thing, the cosine of theta, that entire thing squared? So what we typically do is we put that 2 here, as opposed to having to add those extra set of parentheses. So I want you to get used to this and know that, hey, it just means this. Okay. So then, hey, why is this called the Pythagorean identity? Well, if we think back to what we just really did, was if I drew in my triangles, if I put in this here, I did this squared plus this squared equals this squared, right? My cosine squared plus my sine squared equals 1 squared, which is what we have right there, right? It's really I do the Pythagorean theorem on that particular right triangle, and I can normalize it to being for any angle that I have, and I get this thing here, which is going to be a very, very important identity for us kind of going forward into the future. You'll typically see it with the sine squared first, but again, the order in which we add doesn't really matter all that much. So let's hop back over to this, and we'll do our closure real quick. So let's take the equation sine of theta is equal to 2/3. What quadrants must it be in? Okay, so if we get a sine value that is positive, okay, where could that be? Right, so let's think back over to our table. Okay. So where is our sine positive? Well, our sine was positive here and here, right? Which over on our circle was in the first and the second quadrant, right? And then if you go, do we know the x or y coordinate of that? Well, I know the y coordinate is going to be 2/3, right? Going back over here, it has to have a height of 2/3. I'm not sure if it's over here or it's over here, but it has to have a height of 2/3. And then how can we solve for the other coordinate? Well, I could do the Pythagorean identity we just did, right? If I know the value of the sine, I can then go in, square it, and solve for the cosine, and what I'll actually get is the 2 possible points where it could be, right? And then what would the value of tangent be? Well, tangent would be that sine over that particular cosine. So with that, that's going to be it for this lesson. Here is our homework. 64 through 71, go ahead and give those a go, and I will talk to you guys next time.